This lesson is the introduction to plasma art cutting. We're going to spend just a few minutes going over the basics of how plasma art cutting works in preparation for your work in the lab. The picture on this first screen is actually from a plasma cutter that is cooled by water. That's slightly different than ours. Ours is cooled by air, but the logistics are the same in that we have a power source coming in and we use plasma, which is often referred to as the fourth state of matter, to cut through the metal. It is a very useful part of the welding industry and in many shops is replacing the use of oxyacetylene because of the simplicity and the lower cost. Throughout this slideshow, I've highlighted the things in red that I feel like are most important for you to capture in your notes. First off, you need to know that plasma art cutting was actually originally designed to cut non-ferrous metals. It later was kind of adapted, if you will, to cut steel. And there's some kind of historical rumors and a little bit of proof that the Army was using plasma cutting in World War II, but it really wasn't available to the rest of the industry until the late 50s. And I believe it was in maybe 1957 when a patent was finally established and it became produced widespread. As we see this technology continue, I think you will see it continue to replace older cutting technologies. There are really only a few situations where it's not very useful, and that would be where there's no electricity available because it does use an electrical power source. There are some big advantages over plasma art cutting over oxy-fuel cutting. It's significantly faster, and when I say use the word faster, I mean faster to learn and faster to do. You can actually progress faster through metal when you're doing that. As long as it's done correctly, the kerf is more narrow, meaning it takes less metal out of the original metal. Typically the kerf or the cut is a lot cleaner. It has a little bit more diversity in that it can cut both ferrous and non-ferrous metals with just slight adjustments to your amperage. And as long as electricity is available, it's actually far more economical. A few years ago, they stopped acetylene production in the United States for the most part when a large facility blew up, and so now we're paying quite a bit of traveling and transport on gases like acetylene, and that makes kind of a big deal to the cost. One of the big advantages to fabrication shops of oxy-fuel cutting is that there's less warping of the base metal. And so this means that whatever you cut won't have bends related to the heat, and it's going to be a little bit easier to fab up. This is a picture that kind of demonstrates what I was talking about with the warpage. In particular, I want you to pay attention to the bottom of the screen. When you cut with a torch, you can see that kerf takes more out of it at the top than the bottom. And that has to do with just the way heat works when oxygen and acetylene are combined. A plasma cut tends to be a little bit more consistent all the way through. The top pictures in this slide show how metal looks obviously at first, and then when it's heated, it bends towards the heat. And so we see that happen as you're cutting, which means you, for all intents and purposes, can't have a clean kerf. As that metal cools again, it bends away from the heat. And so when you use oxygen and acetylene to cut, you're really just hoping that it kind of evens itself back out, and that doesn't always happen. When we go to the dictionary, we see that the word plasma has two meanings. Probably the more widely accepted in society is the idea that plasma is the fluid portion of your blood, and there are places where you can donate or sell plasma. It's rather important to many medical treatments, but for the purposes of this lesson, we're going to talk about that plasma is a state of matter that is found in a region of an electrical discharge. The basic premise here, and this is what I'd like for you to put in your notes, is that when you're plasma arc cutting, you pass an electric arc through a gas. The gas is restricted by a nozzle, and so that pressure and heat together changes this into a high energy state called a plasma, and it basically acts as a solid cutting through the metal even though it's not a solid. That's a picture of what they call a plasma ball. You can buy them on Amazon if you want to kind of see how a plasma really looks when it's happening. But the scientific basis behind it is that through heat and pressure, atoms either lose or gain excessive numbers of electrons. And so this kind of extremely charges it positively or negatively. These bonds are a little bit stronger, and they cause the gas to bind. And so that's the science of what makes it act like a solid. We actually see plasma all around us. Low temperature plasmas are used in things like fluorescent lights. And so we use this in a lot of society. We're just using it in a different way when you cut with a plasma. Some of the places you might see plasma are in like neon lights and then fluorescent lights. But these last two pieces on the bottom of the slide are probably the more important part, and this is what I want you to record in your notes. When we arc weld, well, first off, let's start with oxyacetylene welding and cutting. When we operate those gases together, we're looking at a temperature of like between 3,000 and 5,000 degrees. When we bump that up to an arc welder and we harness that electricity to create an electrical arc and then weld with it, we almost double that to 6,500 or about 7,000 degrees. But when we create a temperature with a plasma arc, sometimes those temperatures where the cut is made or where the arc is, if you will, go up to about 25,000 degrees, between 20 and 25,000. The interesting part is, though, is that heat is very localized. So whereas when I cut with an oxyacetylene torch, it's going to preheat 6 to 8 inches of the base metal on either side of the cut, a plasma arc does not do that. And so the amount of warpage is far more minimal, and it's a little bit easier to manage. I'll provide a paper copy of this diagram for you, so don't worry about drawing it. But I do want you to just kind of look and process that a little bit. In terms of what the components of your station look like, it's a medium-sized machine that can be carried around. We plug it into a constant current DCE and power source. You can have plasma torches that run via 110 or 220. The amount of electricity used is directly correlated to how thick of metal you can cut. As we go down the torch lead to the torch body or the torch head assembly, you can see kind of a cutout of it at the bottom of the slide, where we have the electrode, which then goes through a gas distributor and into the tip, and then has a shielding cup over it. That shielding cup is truly just to shield it from spatter and things like that. The electrode is very uniquely shaped, and we'll look at pictures of that here later in the slideshow. But it basically, through the torch body, is going to control that gas and make it do what it needs to create plasma. As we mentioned before, plasma arc cutting can be either water or air cooled. That oftentimes depends on the size of the facility, what is available, and so we have some gas hoses, and those could be water hoses in some places. There is air filters needed when we're air cooling, in part to take the moisture out of the air, and you can get those in all different types of kinds and shapes. You will notice that you need to have a ground clamp hooked up. You can see the ground clamp in the picture there, and that we have the control panel obviously on the front. Usually those regulators and filters and also air gauges are on the back of the plasma cutting station, and so that's where you're going to make some of your adjustments. This is kind of the electrical diagram, if you will. You can see the power source off to the left, and how that comes, from the negative through the electrode, surrounding and kind of spiraling around due to the shape of the electrode is where the orifice gas comes through, and then that goes through the nozzle and cuts through the workpiece. It's that ground on the workpiece that then goes back to the positive on the DC power supply and completes the circuit. This is an up-close diagram of what the torch parts look like. I bring this back up only so you understand which parts of the plasma torch are your consumables, if you will. We mentioned in class, and I think it's pretty cool to even reflect on my short lifetime how much the plasma torch parts have changed in both style and cost. When I was right out of college and ran a plasma torch, the tips were such that every time I bumped the metal, I would foul a tip, and they were quite expensive. Now the tips have been changed, and many of them are drag tips. That's what we're using, meaning you can drag it on the metal. And as long as you don't have spatter coming up and clogging your orifices, you're probably fine. But we do know that we have to replace the tip and the electrode periodically. So we know to replace the electrode when the tungsten that's in the middle of it wears down enough you can't strike that arc again, or it's not striking well. And then the tip, we're going to worry more about the roundness of that orifice and that it has maintained its original size. This is what a good tip and a bad tip would look like. You can see that once you begin to cover up part of that hole or orifice, you have a hard time controlling the arc, and so you want your arc to be pointed and focused in the right direction to make it clean cut. Most of the newer electrodes have an element of tungsten in them, and we see that electrode is spiraled in shape to create a swirling motion, and that concentrates the arc to work in a more straight and narrow plasma stream. In this diagram, the cutting gas and or the shielding gas, sometimes they're the same, sometimes they're different, are in kind of an orange color. And then you can see that the piece where the plasma stream is created and cuts through in such a narrow way. You can use a variety of gases to cut with a plasma torch. The most common one in shops that have to use it in tanks is nitrogen. We actually use compressed air because we have an air compressor available and we're in a stationary shop. You can also use oxygen. Some things that might determine which plasma gas you want to use are cost and location. So what's available to you and what is your budget there. When you are manually cutting with a plasma torch, and let me back up here and say that you will later in this class, potentially next year, learn how to operate the plasma torch with a computer. So when we use a CNC type system, we can program the computer to tell the torch to go in certain places at a certain speed and cut out things in a very consistent basis. It will do it with a basic piece of artwork, but man, you can fabricate up different parts and signs and lots of industry-wide important things. We're going to be cutting manually right now, which means that you're controlling the torch with your own hand. And so there's a few things to consider. One is that it does still produce ultraviolet rays. They are not as intense as arc welding, so sometimes people get a little lackadaisical about that, but you really should have a shade 8 lens or higher. In our shop, that would be those oxyacetylene shields. You need to make sure your air supply is clean, free of oil and moisture. We typically change out our air filters on the back of the plasma torches every few years. You need to have a minimum level of air pressure. This is probably most articulated to you when you have to come down and let the compressor run just a little bit before you run the plasma torches. I think you'll see that change when we move into the new shop and we have a little better plasma or a little better air compressor location. But most plasma torches require a minimum air pressure of 35. 50 is more recommended. Because we're running 2 off of the compressor we're using, I'd like for you to wait till that gauge reads 80 before you start cutting. The current should be adjusted somewhere between 12 and 29 amps. This is pretty highly variable because it's so dependent on machine. The machines have progressed so quickly over time that it doesn't always kind of mean the same thing in the same brand of machine. But the piece that you have to really focus on as you begin doing this operation, if you will, is that you control 3 basic things. Once your machine is set up and running, you control the speed at which you move forward, the angle at which you hold your torch, and the length of your arc. Now, we'll talk a little bit about how to do settings on your machine, but you should remember that it's highly dependent on machine. So I actually took out the graph or the chart that I used to keep in here, because if you look in the manual with the plasma cutter you're running, those charts will read differently across the board depending on your machine. So there's a few things you can keep in mind. One is that you want to do some experimental cuts, but obviously the thicker your metal, the higher your amperage needs to be. You need to pay attention to what that machine claims it can cut through. For example, the machines we're using are not meant to cut anything more than 1/2 inch. I even see them begin to be more difficult to cut on, anything over about 1/4 inch. The tips that we're using are drag tips, so you're going to keep your tip either dragging on the metal or about 1/8 inch above it. And many of you have heard me say, as we did initial demonstrations, that part of what you're going to watch is where your sparks go as they cut through. And if those sparks are bouncing back, that can be a very quick indicator to you that your speed is off or your arc length is off and you need to adjust because it's not actually cutting. So those are a few of the things that you're going to pay attention to. One of the important parts about a plasma cutter is you really can directionally cut in any direction, and that opens up some ease of creation for you, that you can go forward, you can go left, right. It's not as picky as some processes. So I hope this gives you enough basics that you can get started and cut different thicknesses of metal, different types of metal, and be successful in those endeavors. Have a good day.